The purpose of this video is to provide an overview of the Dark Matter Lab. Let's begin in the module. We'll scroll down till we find the Dark Matter Lab. There are two files here that we need to download. We need to download the PDF file and we need to download the data file, which is a .xlsx Excel file. You can see there's also questions here. That's where you upload your completed Excel file and you also answer the follow-up questions. Let's download the files and then open them. Let's start by looking at the template file. The purpose of this lab is to determine the amount of dark matter that is present within a program galaxy. The things we're going to need the template, which is the file we're looking at right now. We're going to use Excel. We're going to need the data file, which we just downloaded, and the questions where we will answer our online follow-up questions and upload our completed Excel file. In the background information, there's a lot of very interesting information about the history of dark matter and what exactly dark matter is. I recommend you read that. There's also a discussion about galaxy rotation curves and what those are and how they show the existence of dark matter. Dark matter is just a name that we call matter that we can detect gravitationally, but we cannot see in any part of the electromagnetic spectrum. There is an equation here, equation 12.01, which we will use as we go through this lab. And you'll notice it says m, which is mass. That's the mass of a galaxy within a certain radius. The radius is r. And v squared, that's the rotational velocity of the galaxy at the radius of r. And then g. G is actually the universal gravitational constant, and its numeric value is given right up here, 4.31 times 10 to the negative 6, and the units are kiloparsecs, kilometers squared per second squared, solar mass. I know that sounds like a weird unit, but it actually works out that way. When you plug in G and V in kilometers per second and R in kiloparsecs, then the mass turns out to be in units of solar masses. Here's also a curve of what's called the mass to light ratio curve. B minus V, color index is across the bottom here, and mass to light ratio is on the vertical axis. We will be using this also in this lab as well. Here's an equation for the mass of stars, also in units of solar masses. The mass of the stars is equal to the mass to light ratio times the luminosity of the stars. Again, we will be utilizing this. And also this. This is really an equation that tells you can figure out how much dark matter mass there is by taking the total mass, that's the total gravitational mass, and then subtract off the baryonic mass. Baryonic matter is matter that we're used to. It's matter that's made out of protons, neutrons, and electrons. That's baryonic mass. Dark matter is not made out of those things. So you take the total mass and you subtract off the mass that's due to the matter that we know, and what's left is the mass of the dark matter. All right, let's get started. Here is the curve that we're going to use. This is a rotational curve for this galaxy that is shown up here at the top. And you'll notice that along the bottom we have the distance from the galactic center. So this is 0. This represents the galactic center, and if you trace that line right straight up, you'll see that it intersects with the galaxy's position right there. That's the galactic center. And then as we go to the right, you'll notice that these units are in kiloparsecs. There's 5, 10, 15, and 20 kiloparsecs. And then to the left, the numbers are negative. So that's negative 5, negative 10, negative 15, and negative 20 kiloparsecs. Okay, and as you go farther out, you're getting farther from the center of the galaxy, so there's about 5 kiloparsecs in the image, about 10, about 15, and 20, and so forth. Okay, and then we have rotational velocity in kilometers per second along this vertical axis. You can see here is 0, and 0 corresponds to the center of the galaxy. And then we've got positive 100, 200, 300, and then negative 100, 200, 300 going down. All right, we're going to use this curve to read off rotational velocities given a specific radius. Next comes the procedure, and we will go over the procedure here in a little bit. There's two parts. And here are the data files. You'll notice there are 3 data files here. Also notice that the radius r in kiloparsecs is in the first column of all 3 of these tables. And the numbers are the same, so negative 20, plus 15, negative 3, and plus 3 are the same all the way down. You'll also notice that some values are already filled in. I'll show you where those values come from when we walk through this. But some of the values are already given to you, and those are in table 12.02. You can see the stellar luminosity within R. That's in solar luminosities. That's given to you. The average B minus V color index of stars that are within the radius is also given to you. And then the gas mass within the radius in units of solar masses is also given to you. And we will need all of those given values as we go through this. And then finally, here are the follow-up questions. Looks like there's 10 follow-up questions here, and we will answer those in the online quiz. Now, here I am looking at the Excel file, and I'll see that there's data table 12.01. There's data table 12.02 with many of the values filled in. Those are the values that are given for this specific lab that you need in order to do some of the calculations. And then here's table 12.03 with it's completely blank. 12.01 is also blank, but 12.02 has many of the values filled in already. All right, so let's go back to the procedure and start the lab. Step 1, rotational velocity. We need to use figure 12.05. That's this figure right up here, figure 12.05. And we need to estimate the rotational velocity of the program galaxy at each of the 4 radii that are given to us in data table 12.01. So if we come up here, if you remember, let's look at that. Look at the data table one more time. The first radius is negative 20. The second is plus 15. The next one is negative 3 kiloparsecs. All of these are in units of kiloparsecs. And the next one is positive 3. So negative 20. Let's look at radius of negative 20, and we need to estimate the rotational velocity in units of kilometers per second from the rotational curve. So here is the rotational curve for our galaxy, for our program galaxy, and negative 20. That's this out here. Now I've turned on my highlighter. It looks like right at negative 20 here, somewhere right around in there is where the rotational velocity is. So here's negative 200 and then negative 300 down here. And if I count, there's 1, 2, 3, 4, 5 increments between 200 and 300. Now, by my estimate, it's approximately 225. And because it is down here, it's going to be negative. So negative 225 is what I am going to put in here into the rotational velocity, negative 225. Now you will need to do that for the other radii. So for 15 kiloparsecs, that's positive 15 kiloparsecs, you'll come back here to positive 15, which is over here, and you'll trace it up and you will make an estimate. What do you think that value is right there? Now you'll trace it over here to the right hand side, and it looks like it's not going to be 225, might be a little larger. You make that estimate based upon what you think the answer is. And then you will need to do that for all of the other values in this table here. Okay, now that I have a rotational velocity, now I need to compute the total gravitational mass within the radius. And if you will go back up here to the first equation, this is how you calculate the total gravitational mass within the radius. The v is the rotational velocity that we just calculated. The r is the radius, and then g is this value that's right above there. So we need to calculate that in our Excel spreadsheet. Now here's the way I can do that. I can use an equation, I can use a formula. I want to take this value and I want to square it, so I'm just going to multiply by that value twice. Then I'm going to also multiply by the radius here, and I need to take the absolute value of that radius because the mass always is going to be a positive value, so I'll take the absolute value of that. And then we're going to divide by our g value. Now g was 4.31. E, we're using scientific notation here, so E and then -6. And there I see I have a value of 2.35 times 10 to the 11th, and that is in units of solar masses. So there's 2.35 times 10 to the 11th solar masses within a radius of 20 kiloparsecs from the center. All right, you will use a similar equation to calculate the other gravitational masses within radius r. Be sure to use the correct radius and also your rotational velocities that you determined. All right, so if we go back here to the procedure, we have just done step 1. We've also done step 2. Now we're ready to move on to step 3. Step 3 is just take a few minutes to familiarize yourself with the second data table, and you'll notice that the 4 radii are exactly the same, and there's a lot of already filled in values that are given to you in data table 2. We've already pointed that out. Now the stellar mass to light ratio is something that we need to determine, and in order to determine the stellar mass to light ratio, we need to go back here to our graph of this. Now when I look at data table 12.02 here, I can see stellar mass to light ratio, that's solar masses per solar luminosity, is not filled in, and I need to do that. But I am given an average B minus V color of the stars that are within the radius, and for this top one, it is 0.35. That's the average B minus V. So I'll take that 0.35 and I'll come over here along the bottom of this graph and I will find 0.35. Now it looks like there's multiple marks between 0.3 and 0.4, and looks like there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 marks between 0.3 and 0.4. So I need to go halfway in between. So my estimate, when I have a B minus V color index of 0.35, I trace over here to the left and I estimate the mass to light ratio to be 0.45. Now you may get a slightly different number, but there is a range of acceptable values here. If you were to say it's 1 or 1.5, that's obviously wrong. If you said it's like 0.2, that's probably also obviously wrong. So somewhere around 0.45, that's my estimate. So that's what I'm going to put in my data table. So I'll plug in 0.45 right there. 0.45 is my estimate. All right, let's go back to the procedure then. We just completed step 4. Now we're on step 5. Let's figure out the stellar mass within the radius r. We're going to use equation 12.02 along with the stellar luminosity and the mass to light ratio that we just found to calculate the stellar mass within each of the radii. So let's go find that equation. And here it is. This is going to be the mass of the stars, also called the stellar mass within the radius. We have the mass to light ratio. That's what we just determined to be 0.45. And we're going to multiply by the luminosity of the stars, which is another one of those columns that were given in the data table. So I'm trying to fill in this cell here. This is going to be equal to the mass to light ratio multiplied by the stellar luminosity. And there. I end up with 1.31 times 10 to the 10th for my stellar mass within radius r. Now that's all the stars that are there. We also have to consider the amount of gas that's within that radius. And then both of those, the stellar mass plus the gas, that represents the baryonic mass that's within the radius. So this last column over here, the baryonic matter within the radius, is actually just the sum of the stellar mass plus the gas mass. And that turns out to be 2.51 times 10 to the 10th. All right, and we just filled in this entire table here for the negative 20 kiloparsec radius. Okay, let's go back to the procedure then. We determined the stellar mass within R, and then we also just filled in the baryonic matter that's within R. You need to do that for all of the blank cells that are in data table 12.02. Now let's analyze the data. It says the data you gathered in part 1 can now be analyzed to determine the mass of the dark matter. And we're going to fill in values that are in data table 12.03. First thing we need to do is we need to transfer the values for the baryonic matter, that's the stars plus the gas within the radius, from the last column of data table 12.02 to the second column of data table 12.03. So let's go do that. Okay, so this is data table 12.02. This is the baryonic matter within the radius. I want to copy the things in this column to 12.03, the second column here. So I want to copy those there. Now you can do this, you can just say it's equal to, and then go back to that previous cell and click on that, hit enter, and there, it copied it for you right there. All right, now step 8 says that we need to also transfer the value for the total gravitational mass within R. Now that was something that was back on table 12.01, and we need to put that in the third column. So we're going to transfer both baryonic matter and total gravitational mass. So let's go do that. The total gravitational mass, this is what was on the first table, so let's put equals, and now go back to 12.01, that, and now hit enter, and there, it's filled in for me. Very nice. You'll need to do similar things for the rest of these columns here. And now the next step is dark matter within R. Let's go back to the procedure. Step 9 says compute the amount of dark matter within R by subtracting the baryonic mass from the gravitational mass. Okay, so here we are. The total gravitational mass is going to be greater than just the baryonic mass because the total gravitational mass includes dark matter. So what we want to do is we want to equals this number, and then we'll subtract off this number. Now, it should be a positive value. You should have positive values for everything in all of these columns on this table. But just to make sure, I'm going to take the absolute value of it, like that. Okay. Now that didn't change our answer because our answer was already positive, but what it does is it ensures that numbers here, especially if I copy this formula on down, that all of the numbers are going to be positive. Just in case somewhere along the way you make a mistake, just keep in mind these should always be positive. All right, then it looks like percent of total mass due to baryonic matter, and then the percent of total mass due to dark matter. Let's go back to the procedure. Step 10, divide the baryonic matter mass by the total gravitational mass. The total baryonic mass is this one, and the total gravitational mass is this one. So let's equal that divided by that. And looks like it's 11%. Now this was already, for me, this was already in units of percent, but if it's not for you, you can go up here and you can change this to be percentage here. It says it's 10.66, but I just want it to be rounded to 11%. Okay, now we need to do the same thing for the total mass, percentage of total mass that's due to dark matter. So this will be equals the amount of dark matter divided by the total mass. And once again, I've already set this up to be in units of percentage. If yours is not, you can change it again by the same method. And I am not displaying any decimal points here. So 89%, that means that 89% of the mass of this galaxy at negative 20 radii is dark matter. That means the galaxy has much more dark matter in it than it does regular matter, matter that you and I would recognize as matter. So that's a large chunk of this galaxy that is unseen, undetectable matter, undetectable in the sense that we can't see it or detect it in any part of the electromagnetic spectrum. We can only detect it gravitationally. As you go through this and you fill out the rest of this table, you should discover that the numbers are in that same ballpark. You will always have the percent of total mass of the dark matter greater than the total mass due to the baryonic matter. In other words, this F column should always be a lot larger than the E column as you go through this. All right, and let's see what's left. I think we've completed the procedure at this point. All that's really left is to answer the follow-up questions, which you can do in the quiz. You will want to be sure to save your completed Excel file. Be sure that you check it before you upload it, just to make sure that you're uploading the correct file. All right, I hope that helps, and I hope you learned something along the way here. Have a great week.